Now we are going to start talking about how to make a decision. First, we will ask what is involved in making a good decision. With the decision models we talk about this week, we can make rational choices based on analysis instead of arbitrary choices with unknown consequences. Decision theory is an analytic and systematic approach to the study of decision making. A good decision is one that is based on logic, considers all available data and possible alternatives, and applies a quantitative approach. The 6 steps in decision making is drawn from the 6 steps of rational decision making, which is a psychology theory. It's very similar to the quantitative analysis approach, where you're going to start with defining the problem. After we understand the problem, we are going to list our alternatives. These are our different decisions we can choose from. Let's say our problem is we have some money we want to invest. Our alternatives would be the kinds of investment we would make, such as to invest in stocks or bonds, or to not invest at all. That would give us 3 alternatives. Now, how would we choose between those alternatives? How would that choice be affected? The next step in the process is to identify the states of nature. For investments, the states of nature would be either a favorable market, where the market goes up, or an unfavorable market, where the market goes down. Next, we will list our payoffs for each alternative in a particular state of nature. Basically, how much do we expect to make or lose for a particular choice we make? We are going to go over several types of decision models. At this stage, we will select a decision model and then apply that model to make our decision. We define our problem as whether Thompson Lumber should expand their product line by manufacturing and marketing a new product line, storage sheds. 3 alternatives have been identified. They can build a large manufacturing plant, they can build a small manufacturing plant, or not build a plant at all. There are 2 possible states of nature: a favorable market, where lots of people buy storage sheds, and an unfavorable market, where few people buy storage sheds. Now we list the payoffs for each combination of alternatives and state of nature, which we will see on the next slide. We will see which decisions should be made based on the applications of 5 different decision models. This is what our payoff table looks like. We will structure each of our decisions based on a payoff table, just like this one. Which decision would you make without any prior knowledge? We have 3 types of decision-making environments. Decision-making under certainty, where the decision maker knows with certainty the consequences of every alternative or decision choice. Decision-making under uncertainty, where the decision maker does not know the probabilities of the various outcomes. And finally, decision-making under risk. The decision maker knows the probabilities of the various outcomes. With decision-making under certainty, we know for a fact which state of nature will occur. If we know for a fact that we're going to have a favorable market, then we would select to build a large plant because it has the highest payoff. However, if we know for a fact that we will have an unfavorable market, then we would select to do nothing because we would lose $0. If we are uncertain about the state of nature, whether there is a favorable or unfavorable market, then we are in an environment of decision-making under uncertainty. We have 5 potential decision models in this environment. The first model is for optimistic decision makers, are those that have a positive outlook for the future. These decision makers believe that there is a high likelihood of a favorable market. The model is called Maxi-Max, which is the maximum of the maximums. First, we take the maximum for each row, then take the maximum of that new column. You can see our decision circled in red on the slide. Using Maxi-Max, we would select to construct a large plant, because we would maximize our profit and make $200,000. Model is for pessimistic decision makers, or those who have a negative outlook for the future. These decision makers believe there is a high likelihood of an unfavorable market. The model is called Maxi-Min, or the maximum of the minimums. First, we take the minimum for each row, then we take the maximum value of that column. In this model, we would select the alternative to do nothing, because we would lose $0. The criterion of realism, also called the Hurwitz model, tries to balance between optimism and pessimism. In this decision model, we select an alpha coefficient based on how confident we are in a favorable market. Let's say you are 70% sure of a favorable market. Now, you need to be careful about the percentage here because you are making this percentage up. If you are given a probability, then we will use a different model. Now we take our 70% and create a weighted average for our favorable market. For the unfavorable market, we will take the complement of our favorable market, which is 1 minus 0.7, or 0.3, which means we think there is a 30% chance of an unfavorable market. For Thompson lumber example, they decided that there is an 80% chance of a favorable market. To calculate our weighted average, we multiply 0.8 times the payoff for our favorable market and subtract 0.2, the complement of 0.8, times the payoff for the unfavorable market. This gives us the payoff for the criterion of realism. Then we select the maximum payoff from this column. Here, based on the criterion of realism, we would construct a large plant. With the Laplace, or equally likely decision model, we take the average of the payoffs for each of the states of nature. For two states of nature, we add the payoff for the favorable market to the payoff for the unfavorable market, and then divide by 2. We then select the average payoff with the maximum value. The last decision model we will discuss is aimed at minimizing your regret on choosing the wrong decision. This model is called Mini-Max Regret. Take the minimums of the maximums on an opportunity loss table. The first step is to create an opportunity loss table. To calculate opportunity loss, you subtract each payoff in the column from the best payoff in the column. Best is dependent on whether we are maximizing profit or minimizing cost. If we are maximizing profit, then we select the highest payoff for each state of nature and subtract from it all the payoffs in that state of nature. If we are minimizing cost, then we would select the lowest payoff for a state of nature and subtract from it each of the payoffs in a state of nature. In this example, we are trying to maximize profit. So for the favorable market, we will take the highest payoff, $200,000, and subtract each of the other payoffs from it. That gives us our favorable market column. In the unfavorable market, our maximum payoff is 0, so we will subtract each of the other payoffs from 0, and gives us our unfavorable market column. Opportunity loss table to work with. We then apply the minimax decision model, which is the minimum of the maximums. So we take the maximum in each row and then take the minimum value. In theory, this should minimize our regret from choosing the wrong decision. In this instance, we select to construct a small plant. So what is risk? It is not just a board game. It is a situation involving exposure to danger, harm, or loss. In the business context, we will say risk is the potential for monetary loss. Decision-making under risk involves probabilities. In this case, we will be given the probabilities. This is what differentiates these set of models from Hurwicks. In Hurwicks, you selected the probability in decision-making under risk. Someone else tells you the probabilities. The most popular model in this category is to calculate the expected monetary value. EMV, we multiply the payoff for an alternative times the probability of that state of nature, and then add the payoff times the probability of the next state of nature, and so on, for each state of nature. Back to our Thomson lumber example, let's say there is a 50-50 chance for a particular state of nature. We multiply 0.5 times the payoff of the first state of nature, which is 200,000, and we add to that 0.5 times the second state of nature payoff, which is negative 180,000. We add the values together to get an EMV of 10,000 for the first alternative. We do this for each of our alternatives. We calculate the EMV for each of our alternatives, and then we select the alternative with the maximum EMV. In this case, our best EMV is to construct a small plant with an EMV value of 40,000. This is the most important concept in this class. As a manager, you will have additional questions after your analysis. In this case, we may want to know how we need to adjust a payoff value in order to change the alternative we would pick. In this example, we selected a small plant, but what would the payoff need to be in order for us to justify the alternative of building the large plant? If we set the favorable payoff to x, and set the EMV equation equal to the payoff of the alternative with the highest EMV, we can then solve for that payoff, or what the payoff should be. At this point, we can now choose a small plant or a large plant if the large plant's payoff was 260,000 instead of 200,000. So how much more would the favorable payoff of a large plant have to be in order to increase our likelihood of choosing the large plant? Well, basically, we would need to increase the payoff for building a large plant in a favorable market by 60,000. If we cannot expect this to be a feasible payoff, then we should still select the small plant. The expected value of information is the most that you should pay for information that will assist you in making a better decision. The expected value with perfect information is the long-run average if you make decisions based on perfect information. We need the EVWPI in order to calculate our EVPI. To calculate EVWPI, we take the best payoff for a state of nature and then multiply the probability of that state of nature, and then sum these together. For two states of nature, we would have two values summed together. To calculate the EVPI, we take our EVWPI and subtract our best EMV. Back to our Thomson lumber problem. If a marketing firm offered to provide certainty of a favorable market, what would be the value of that information? This information would cost $65,000. Is it worth it? We calculate the EMV on the first 3 rows and find the best EMV is 40,000 for a small plant. Next, we calculate the EVWPI. The best payoff for a favorable market is 200,000, and the best payoff for an unfavorable market is 0. So we multiply the 200,000 times the probability of a favorable market, which is 0.5. This gives us 100,000. Then we multiply the probability of an unfavorable market, 0.5, times 0, which gives us 0. Then we add those together. So 100,000 plus 0 equals 100,000. And that gives us our EVWPI. Our EVWPI is 100,000. We subtract our best EMV of 40,000 from our EVWPI and find that the EVPI is 60,000, and thus the most we should pay for perfect information is 60,000. The marketing firm wants us to pay 65,000, which is more than our EVPI, and thus Thompson Lumber should not pay for this information. An alternative to maximizing EMV is to minimize opportunity loss. To simplify this, we're doing the Minimax regret model, but we're doing it on an opportunity loss table and calculating out the EMVs. But an EMV calculated on an opportunity loss table gives us our expected opportunity loss. To calculate this out, we do the same as we did before and the expected opportunity loss. So it's the same way we calculated the EMV, where we subtract the best payoff, or we subtract from the best payoff each of the payoffs of that state of nature. We multiply it times the probability, and on the opportunity loss table, that'll give us our expected opportunity loss. Then we take the minimum EOL value, and in this case, our best expected opportunity loss is 60,000, so we would construct a small plant.